We're going back to school, guys. We're going to make a course schedule. There are a total of so many courses that you have to take. You have to. And they're labeled from 0 to n-1. You are given an array of prerequisites where it's a tuple. So this second item is a prerequisite for the first one listed there. And it indicates that you must take B before A. Then they give an example, and then you return true if you can finish all the courses, or return false if you're a big fat failure and your parents are disappointed. Well, they're disappointed anyway, but all right. I actually kind of like this one. I didn't do a practice run, but we'll see how it goes. The basic approach is, okay, at first glance, course schedule is kind of a red herring. It makes me think of interval overlaps and that kind of an algorithm. But it's not that. It's not that at all. It's actually a little bit of looking for cycles in a graph. So if you think of, it's not exactly a linked list. It's really like a a linked graph or whatever. You're looking for cycles in a graph. Being, if you've got some, it's linking all the things together, and you eventually want to find if something is its own prerequisite. So if they give a negative example here where you've got basic, this one's a circular dependencies. And what you do is you can start traversing from either one and you find that it's its own prerequisite. So if you start from number 1, if you start from class number 1, okay, you have to take 0 before that. So let's see what 0 is and traverse, that. Okay, well, 0, that requires 1 first. So, but if we look at if we keep track of our visited nodes along this traversal, we'll see, oh, we've actually already visited 1. It's a prerequisite for where we're currently at. So then you'd return false. Let's go ahead and, well, yeah, okay, so the target runtime we're looking at, if we're doing something like that, obviously we're looking at linear time. No matter what, we have to look at every prerequisite tuple, which is realistically, okay, there's 2 types of inputs. Linear time would be on the number of prerequisites. And then realistically, the number of courses themselves it's almost kind of irrelevant, because if there's a bunch of courses and no prerequisites, then obviously you can finish them all. If there's a bunch of prerequisites and no courses, I don't know if that's really a case. Okay, so the number, let's see. The number of courses, there's up to 2,000 courses. There's up to 5,000 prerequisites. You could have a crap ton of prerequisites. And and then this is the key constraint here. I think this means the number of this is saying that the prerequisites themselves will only apply to the courses that exist. So you never can have prerequisites listed that are higher than the number of courses, meaning you're not going to have irrelevant prerequisites. All of the prerequisites will put some constraint on the courses that you're actually considering taking. All right. Okay. Anyway, depth first search or graph traversal is going to be linear time, especially if you're building a graph from this. And we're not going to do any sort of depth first. We're not going to, the size of our graph that we build is not based on the number of courses available. It's based on the prerequisites. Meaning we're not going to hit some sort of NP hard situation where you can have a really, really, really high value number of courses, and even if there's only a few prerequisites. So for example, knapsack is the quintessential first problem that students might learn that's actually NP hard, even if that's not like a concept they tell you at the time. It's NP hard because it's based, knapsack is the hard because it's based on a value. And what you happen is If it's based on the value of an input, your runtime is actually it's technically linear on the number of bits, or it's logarithmic. Point being, if your runtime is based on an unconstrained value, that value could potentially be infinite, and then you have some has to do with scalability. Runtime is linear on the number of bits, and if the bits grow logarithmically, that means that your I'm kind of rambling. Point being, if it's based on a value, it's not actually polynomial. But if it's based on the size of some structure, then it's actually linear. Okay, that was a lot of egregious detail. Let's go ahead and get started. So we're gonna need a couple things. It's graph traversal. So let's go ahead and construct a graph. It's gonna take. We're gonna do it. I'm gonna do it as a linked list, unordered map, adjacency list format. So we're gonna need a header, include unordered map. Don't do map, do unordered map, because this is gonna have hash-based lookups as opposed to a regular map, which is gonna have logarithmic time lookups. So yeah. And we're gonna have our tree, which is gonna be, let's see, it's a unordered map. What are the inputs gonna be? They're gonna be an integer, and it's also gonna be a vector of integers. So here's, we look up a particular node, and then we see all of its prerequisites and in the adjacent. So the adjacency list, this is the list. And then so we have our graph, I guess. I'm just gonna call it G, lowercase g, capital G. I'm gonna call it capital G. G for graph. And it's gonna start with nothing in it. And what are we gonna do for our visited array? Okay, so it's gonna be a vector. Okay. So I'm gonna initialize it with some stuff. It's gonna be initialize. I think the size comes first, so it would be, and then it's gonna initialize to 0. I think the size comes first. And you know what I said about scalability versus the input value? Well, okay, I think I spoke too soon. This visited array, if we, okay, I need to think about this. I could initialize it up front with, there's a couple ways to do this. I can make this a vector to start out, initialize everything to 0, make it already the size of a number of possible courses, which from a scalability point of view, our constraints could touch on all of the possible courses. If we want to try and get back a little bit of real world runtime, I could instead make it another unordered map. What I need is to keep track of a status of each thing. The status being if we're currently traversing some it's going to be depth first search. Maybe I'll start right now that loop first, and that'll help illustrate what I did, because this visited array is actually going to be pretty tricky. So depth first search. So I need a helper function. I'm going to do void. No, I'm going to do, I guess, true. It's going to return Boolean. And it's going to take a starting node, I guess. So int node. And what is it going to do? Okay, so we've got a couple things going on. If we're going to check the visited array, so if visited, if it's what? So if it's 1, we want that to be a case where we've already visited it and we found it to be satisfactory. There's no cycles. from that particular node. And I think that, okay, okay, yeah, sure. So if it's that, then we would return true. And if it's not, so if visited, here's the kind of an exit case. If it's -1, I want that to mean it exists on the path we are currently on with depth first search, meaning it is a prerequisite to where we're currently at. So if that's the case, we're going to return false. All right, what do we do here? So we're at a current node, so we're gonna set it. So if neither of these is true, we're initializing the visited array to 0, meaning we haven't explored it yet. So we're gonna set it to -1, and we're gonna continue down the path. So for int n in in the graph. All right, so we're traversing the neighbors of our graph, the neighbors being prerequisites. I'm populating this first, and then after writing this function, I'll go ahead and like create the graph in the first place, because that's also kind of an important step. All right. If I guess we probably return if any of the okay, exit condition. If any of the nodes return false, that means the whole thing's false. We just care about the one. But if the worst case scenario is if there are no cycles, then that means that none of the nodes are prerequisites, but we have to explore all of them to know that. So if not DFS n, then we return true. Or sorry, return false. And if that doesn't happen, then we can go ahead and mark this node as visited so we don't explore it again later. Then we'd run forever if we don't. Okay, so if, or not if, visited node, 1 for good. Cool. Okay, I think it's probably good there. Let's go ahead and I'm gonna make the graph first, and then this actually I think needs to be I need to move this out to the scope here. Visited. Okay. Yeah, and we declare it, so visited. And it's gonna be a vector of integers. Yeah, okay. This is declaring it as a more like broader scope, so it's available to the helper function. And then here's where it just actually gets allocated. Okay. I'm gonna make the actual tree. So graph 4, 4, 4, 4. And okay, so it's 4 for each prerequisites. So I'm just gonna call it P, I guess. Keep it short. P and prerequisites. Oh my gosh, I hope I spelled that right. Let's do this. Copy it over. Actually, I think I did spell it wrong a little bit. Okay, so for each thing in the prerequisites, we're going to append. So append. G of the first one, P of 0, and pushback, not append. Pushback is the correct term, so we're going to push back P of 1. And I think that'll do it for building the graph. It says all prerequisite pairs are unique, so we don't have to worry about deduplication. Okay, cool. Good. All right. And then for, let's see. Do I want to loop the number of courses or through the entries and prerequisites? Realistically, I think I'm gonna loop through the prerequisites again and just take the first one. That way I don't have to loop to the number of courses. So for vector int, okay, so I'm looping through the prerequisites again, and I'm only going to loop through the first one now, because the first element in each pair corresponds to a root level in our graph. Yeah, pretty much. So if not DFS, P of 0, return false. And I think we can just return true at the end. Hopefully, maybe we'll see how it works out in the example in a bit. Is there anything else that I need? Actually, this might be all right. So let's step through an example. It's DFS, so we're expecting linear on the number of edges and nodes. So it's O of V plus E time and O of numCourses space. We could probably get this space complexity down a little bit. All right, so the time is for building the graph. So this is building the graph and then doing depth first search through it. And the reason we don't have, yeah, so we're using this visited array, so it's still just linear. The space is, I feel like this could be better. This could be better. But then again, okay, there could be, in each prerequisite pair, there could be an actual like prerequisite. So the second element, there could be more of those than there are in the first one. So realistically, I think the upper bound is probably similar. If there's like a giant number of courses and like a few prerequisites, that's pretty awful. Okay, here's a cheese element here. So they give these constraints. If you know for a fact the number of courses is less than 2,000 and you know for a fact the number of prerequisites is less than 5,000, well, that's a known quantity. So your runtime becomes constant because you have a constant size. That's kind of a cute answer, but we'll still talk about it as if these values could be any size. The inputs could be any potentially infinite sizes. We'll keep it that as our kind of hypothetical situation. Okay, so we're gonna and over time and O of numCourses, which could be space where O of where numCourses is okay. The number of prerequisites. So is less than or equal to the number of courses. So this is a tighter bound. This is the broader bound. If we could get it to prerequisites instead, that would be nice. But we do have this relationship where this is the less than or equal to. So realistically, I guess it kind of washes out. I keep harping on this, but I think it's an important distinction. And it really helps you set your target runtime. Okay, example. So we've got our we've got our unordered map, our graph. So we've got a visited array. Visited array is gonna be this. So we initialize that to 2. Visited array is 2. I got our graph, so let's build the graph. All right, going through prerequisites. So we got 1, give it a prerequisite of 0, 0, give it a prerequisite of 1. I'm doing this second example here because this one's pretty trivial. I don't like this example. And honestly kind of want to do a, I'll go through this and decide if I want to do a harder one, but probably not. All right. We built our graph, push back, just the 1. All right. And now we go through the prerequisites. So we're looping through this now, the keys in the prerequisites. I'm gonna do DFS. So start with this. We've got our stack. So I want to make the stack. Stack is looking at 1. All right, so we're passing 1 into this node value. Our visited, that's still 0, so neither of these are going to trigger. We set it to -1, so visited. Wait, let's write names on these. All right, visited and call stack. So this is now -1. For G and the neighbors, so we're going to call DFS on the neighbors, so it's 0. All right, back to the top of here. And we're currently, okay, so visited, call stack 1, now we're on 0. So now passing in 0, the neighbors, so visited of 0, still 0. So neither of these triggers. So we're going to change this to -1. And now we're going to look at its neighbors. So 4 and in its neighbors, 0 has a neighbor of 1. So we're going to call DFS on 1. So now our call stack is at 1. If visited, well, now we have the case where visited of 1, well, it's not 1, so that's not going to trigger, but it is -1. So this case here, the second case is going to trigger, and we're going to return false from this function. So we'll pop that off our call stack. So just a reminder, now node is 0. So we're returning from here because there was the 1 neighbor, and we returned false. So we're going to return false from here. And then we're going to pop that off our call stack. And now we're back to the prior call. We're looking at, okay, 1, our node value is 1. And it's the same deal. We're visited of 1, so this guy. We never changed anything back to regular 1, so they're both still -1. Visited of 1, so this is -1. We're going to return false. Yeah, I guess we are popping a few ways off the top of the call stack. So realistically, I could probably get back some real world runtime by putting a global ret equals true, and then I could say like if not return. This might get back some real world runtime, because what you just saw is, okay, we got all the way back to, we're doing these checks on the visited array a couple of times, maybe more than is necessary. We really just need the one exit condition. So then if the exit condition triggers, the entire thing kind of explodes, and we go all the way back to the beginning. And then we can return this, I guess. Okay, so if not DFS, All right, that might do it. Okay, so that's the case. Then we see that this return value is now false. Well, realistically, okay, we're not going to check this unless we're at the top of a call. And what we saw is we were popping back off repeatedly here, so actually that would not mitigate this case. So I don't know that it's necessary. It might run just fine, but I don't think that's going to help with this case here. So actually, I guess I'll remove it. Anyway, going back and forth. So 0 X condition, we see that is visited, return false, and that means we pop back out here. This is going to give us false, so we're going to return false, and we are not even going to explore the node of 0 here because we explored 1 first, so we're not going to explore this again from this top level. And then we're going to return false. Now, do I want to skip exploring something? Would it make sense to skip exploring something from that top level if it's already been visited the once? I'm going to go ahead and submit. We'll first run for syntax errors, and then, yeah, so return. That was part of the removal thing. I'll see if this works. I might, what do I do? G node undeclared identifier G. Oh, yeah, okay. Let's put that out here too, for global scope. And then that's not necessary anymore. So I guess that does it. That'll solve it. Do I want to continue? Well, we talked about runtime. We did an example, submitted it. Can we game? Are we losing out on some runtime by restarting at these top level ones? I'm gonna do some giggles and see if I'm gonna add these here. So these same checks of the visited array. Fix out that spacing. I think that's not gonna change much. Visited P of 0. Yeah, I think, are we gonna miss out on anything? Oh, typo again. It's maybe that works. Does that harm it? Do we lose out on some correctness? Yeah, we do. We lose out on some correctness. Okay. So in this case, we are getting, okay. We're not reverting the visited item of any top level ones. But okay, let me think this through. Suppose I guess, okay, so we are changing, if there's a top level one or okay, if you got some string, so we start with exploring the 0, we start exploring 1 and then the other. Well, we do change this later visited values to like a non-zero something. And then by the time, okay, that's going to change before we get a chance to explore it from the top level of this loop here. And then when we do a call on it, if it's a non-zero value, we're just going to exit immediately anyway. So actually that does take care of it. So actually, I think, yeah, there's checks here are not necessary. They're taken care of here. So I'm going to go ahead and call that good and then mark it off. And then you folks have a beautiful evening.